Okay, welcome back to the lectures on Fourier transform. And now today we will continue the idea of Fourier series for a function which are not a periodic function. So basically this Fourier series representation is given for a function which is a periodic, and now we will go for the extension of this period. So if we let this period goes to infinity, then we will get a non-periodic function, and we will see what will be the representation in that case. So let me just continue with this Fourier series representation of a function. So in that case we had, for a periodic function of period 2L, the Fourier series is given as fx a naught by 2 and k from 1 to infinity a k cos k pi x over L plus b k sine k pi x over L, where this a k and b k, these Fourier coefficients, are given by the integrals. So like 1 over L minus L to L fx cos k pi x over L dx k 0 1 2 and so on. Bk was again 1 over L minus L to plus L fx and sine k pi x over L. And so now the question is that if we want to have a Fourier series expansion, or let's say for example, if we want to have Fourier series expansion of let's say exponential minus modulus x, which is valid in minus L to L. So if we look at the graph of this function, so we have we have a symmetric function because e power minus modulus x. So in this side also we have this, and to get the Fourier series of this function, we will go for its continuation as a periodic function, and so on to this side as well, and then we find the Fourier series as given here. So in that case we will get this representation a naught by 2 and this a k and cos k pi x over L, and this will be valid for this function minus L to L. This can represent this function in this range in this interval. This a k and b k one can calculate with the help of these given integrals. But now the point is that this is the function was given from minus L to L. So as this extension we have, so the function, this becomes a periodic function of period 2L. But now what will happen if we let, so if we let this L tends to infinity, for any L, this we can represent this function by this Fourier series, but this is the limiting case, that what will happen as L tending to infinity. Just note that in that case we cannot have this periodic continuation. In that case we have a non-periodic function. So we will see today that we can still represent this function as L tending to infinity, and then instead of this sum and the series we will get an integral form something, and this is called the Fourier integral, and this will be valid for all x from minus infinity to plus infinity. So this is the main objective of this lecture, that how to represent a non-periodic function with the idea what we had already in the last lecture of Fourier series. So, let me just continue now with this for. So, again we consider any periodic function we denote now f L x. This L denotes the period, because for period 2L we have the following extension. So, f L is a function of period 2L that can be represented. So, that is what we assume, this can be represented by a Fourier series that f L x is a naught by 2 plus n 1 to infinity, and we have a n cos n pi x over L n plus b n, and we have sine n pi x over L. So, this is the Fourier series corresponding to this function of period 2L, and we denote this function by f L x. So, in a more general case, that this f L x we can replace by the mean value of this function at this x. So, if the function is now defined or is discontinuous at x, so we can have here f L x plus and plus f L x minus divided by 2. So, we can have this average value here. Now, the question is that what will happen if we let L to infinity. So, first we assume the non-periodic function, because as L approaches to infinity we will get a non-periodic function obviously. So, periodic function f x, as this f x we denote the limit as L approaches to infinity and the function f L x. So, if we assume this, and now we pass okay, first let us substitute this a n and b n into the function. So, what we have, that this f L x is a naught. So, 1 over L. So, we have 1 over 2 L, then minus L to L, we have f u du. Here we have for a n 1 over L, I take out of this summation, and we have then minus L to L and f u cos n pi u over L du, and then we have this cos n pi x over L, and plus the other term here minus L to L. For that we have f u and sine n pi u over L du, and then the sine n pi x over L. Now, what we do, so the first term we keep as it is, and f u du, plus for the second term here we have these cos and cos. So, cos a cos b, and this plus sin a sin b. So, this we can combine into one cos function. So, we have here n 1 to infinity, n 1 to infinity, and we have this integral minus L to L. Also f u is common to both the integrals, and here we write this cos a minus b. So, we have n pi over L and u minus x and du. So, this is still the Fourier series representation, just we have rewritten in this form, and now we will let the limit L this period L to infinity So, for that we also assume, so let me just write down that if we assume that this integral minus infinity to plus infinity and the absolute value of f u and du converges the first term on the right hand side approaches to approaches to 0 as L approaches to infinity. Let us take a look again. So, with this term as L we let to infinity, since we have here 1 over L and this we assume a finite quantity. So, this will go to 0. So, we have then this f L x, and the left hand side as we take the limit L tending to infinity and we assume that this will be a non-periodic function f x. So, we have now the first term is 0 and then we left with L to infinity 1 over L and n 1 to infinity. We have minus infinity to plus infinity f u cos n pi u minus x over L du. Let's put it equation number 2, that was our equation number 1. So, now there is a trick here. So, let me explain you very clearly. So, L to infinity we multiply by pi here. So, pi over L, and then we have the summation n 1 to infinity. So, this 1 over pi we have to accommodate here. So, 1 over pi and then this minus infinity to plus infinity f u, and we have cos n pi over L and u minus x du. So, now the point is that just for the simplicity, if we assume that this f alpha is 1 over pi integral minus infinity to plus infinity f u and cos alpha u minus x. So, alpha u minus x du, and also we assume that this pi over L term which is sitting here, and also we have here pi over L. So, this pi over L we take as delta alpha if we denote by this. So, what we get after these new notations, and also we note that as this delta alpha approaches to 0 as L approaches to infinity. So, where we have a L approaches to infinity, because we have the relation between this L and delta alpha. So, as this L approaches to infinity, delta alpha approaches to 0. So, what f x we get now? So, f x is limit L to infinity, we have now limit delta alpha to infinity or delta alpha to 0 for this L infinity, and we have pi over L, and that is delta alpha. So, let me put again inside the summation. So, here n 1 to infinity and we have delta alpha, and this 1 over pi and this quantity in terms of this f. So, it is just simply where alpha is, here we have n and pi over L. Pi over L is delta alpha. So, this is n delta alpha. So, we have f n and delta alpha. Okay, so now it is interesting to see that what exactly the summation is. So, this f is a sum function of this alpha for a given x actually. So, what we see now that, okay, let me just write again. So, we have limit delta alpha to 0 and n 1 to infinity, and we have delta alpha f n delta alpha. So, we just look at this summation. So, we have n is equal to 1. So, the value of this f at d alpha. So, we let me start from this. So, 0, and we have here this delta alpha. So, value of this function as delta alpha, so we can have this form of this f. So, let us assume that this is f, this is the graph of this f. So, what we are doing here, that f when n is 1. So, f delta alpha, this value, and then multiplying by delta alpha. So, basically getting this area here, this area, and then again n is 2. So, we summing up with the f 2 alpha. So, we go again alpha, and we add, now we take this integral. So, this area of this rectangle, and so on. So, for the 3 alpha, so here we have 2 delta alpha, we have 3 delta alpha, and this area. So, now the question is that if this delta alpha, we let this delta alpha to 0, and this is exactly the definition of Riemann integral, that if this delta alpha tends to 0, this area which at present we have these this will be here. So, 3 delta alpha and then multiplied by delta alpha. So, area of this rectangle. So, in that case, now if we let this delta alpha to 0, this summation will give us the area under this curve, and that we can write exactly in the integral form. So, this f x is nothing than it is a 0 to infinity, this integral 0 to infinity of this function f alpha d alpha. And now we go back to the original notation. So, f alpha was defined 1 over pi and 0 to infinity, and here we have for the f alpha minus infinity to infinity, we have f u, we have cos alpha u minus x d u and d alpha, and then we can. So, this is in fact we got a representation, and that is already here, that we have 1 over pi and 0 to infinity minus infinity to plus infinity f u cos alpha u minus x d u d alpha. But if we expand this cos, we get another form. So, we have 0 to infinity, and then we have minus infinity to infinity f u cos alpha u cos alpha x plus. So, this I can close here, and then we have again cos alpha u cos alpha x we have here, and then the sin alpha u and sin alpha x will go to the second integral minus infinity to plus infinity, and f u sin alpha u du. So, here du is missing, and then du and sin alpha x, and then we have at the end d alpha for this integral. Now, what we do, that if we assume that this with 1 over pi and this one is a alpha, and again with 1 over pi and 1 over pi, and with this if we assume this b alpha. So, we can write in a compact form that this f x is is 0 to alpha, and we have a alpha cos alpha x plus b alpha sin alpha x and d alpha, and where alpha is 1 over pi minus infinity to plus infinity f u cos alpha u du, and we have b alpha is 1 over pi minus infinity to plus infinity f u and sin alpha u du. So, this is the Fourier integral representation of a function, and now we will go again discuss some convergence issue. So, it is more or less we started with the Fourier series idea. So, the convergence most of the assumptions will remain same, but we have made one extra assumption, and that was that the integral must converge that absolutely. So, let us summarize this theorem. So, we assume that f is piecewise continuous and one-sided derivatives of f exist at each point on every finite interval on the x axis, and let f be absolutely integrable on minus infinity to plus infinity, that is this f u du converges then for each x on the entire axis what we have, that this 1 over pi 0 to infinity minus infinity to plus infinity, and I am writing again in this compact form. So, cos alpha u minus x du d alpha, this Fourier integral will converge to the average value of the function as the case of Fourier, as in the case of Fourier series. So, f x minus and divided by 2. So, we have all other assumptions what we had for the convergence of Fourier series, other than this f should be now absolutely integrable, because we have used in the proof that if f is absolutely integrable, then only we have this representation for the function. Now, we go for the example. For the function, we have f x 0 x and 0 when x is negative, and when x is between 0 and 1, and when x is greater than 1. So, find the Fourier integral representation of f, integral representation of f, and then determine the convergence of the integral at x is equal to 1. So, here if we look at this function here, which is defined from minus infinity to plus infinity, it is 0 on the negative axis, and greater than x is greater than 1, it is again 0. So, we have this is x between 0 and 1, and then we have 0 and also here 0. So, in this case this Fourier series representation in fact is not possible, because this function is not periodic, and we do not have possibility to make it periodic because the function is given on the whole axis. So, we have this Fourier integral representation, and to get that, so we have this f x, we can represent by this Fourier integral representation a alpha cos alpha x plus b alpha and sine alpha x with this d alpha, and we calculate this a alpha, that is 1 over pi minus infinity to plus infinity and f u cos alpha u du. This is 1 over pi minus alpha to, or we can have the function is 0 in the negative x axis and x is greater than 1. So, what we have basically here 0 to 1 and cos alpha u du, or this function was x. So, we have u cos alpha u du, and this we can integrate. So, 1 over pi, and we have this u as it is, and the integral of this sine or cos. So, cos alpha u over alpha, and 0 to 1 minus 0 to 1, the differentiation of this is 1, and now sine alpha u over alpha and du. So, we go further. So, we have 1 over pi. So, when this u is 1, we have sine alpha over alpha, and then 0 it will be 0. So, we have sine alpha over alpha plus 1 over alpha square, and so once we integrate again here, we will get 1 over alpha square and cos alpha u. This will be plus in that case, because minus will come after this integration, and then we substitute the limit. The upper limit will give us cos alpha and then minus 1. So, 1 over alpha square and cos alpha minus 1. So, we have 1 over pi cos alpha plus alpha sin alpha and minus 1 over alpha square. Similarly, we calculate the b alpha, that is 1 over pi minus infinity to plus infinity and f u sin alpha u du 1 over pi 0 to 1 and u sin alpha u du. So, again we integrate by parts. So, we have u with minus cos alpha u over alpha, and these limits 0 to 1 minus 0 to 1, and this minus minus will be plus. So, we have here u will give 1. So, we have cos alpha u over alpha and du. So, we get 1 over pi and minus cos alpha over alpha minus minus plus. So, u is 0. So, this is gone here. So, we have 1 over alpha square and sin alpha u. So, that is when u is 1, we will get sin alpha, and 0 will get 0. So, this is nothing but 1 over pi and sin alpha minus alpha cos alpha over alpha square. So, this Fourier integral representation of that given function is 0 to infinity. We have cos alpha plus alpha sin alpha minus 1 divided by alpha square. So, this was a alpha, and then we have cos alpha x plus this b alpha sin alpha alpha cos alpha over alpha square, and we have sin alpha x and d alpha. So, we can combine this again, 1 over pi 0 to infinity, and this cos alpha x plus sin alpha x will give us cos alpha 1 minus x, and plus this alpha we take common, then we have sin alpha cos alpha x, and cos alpha sin alpha x will give us sin alpha 1 minus x, and then this minus cos alpha x and divided by alpha square and d alpha. Well, so this is the Fourier integral representation of the given function, and now the question was that determine the convergence of the integral at x is equal to 1. So, now the b part, and if we look at the function, this function is not defined at x is equal to 1, but this integral will converge in that case to this average value. So, that is 0 here and 1. So, 1 plus 0 by 2, that integral will converge. So, the function is not defined at x is equal to 1. So, the value of the integral at x is equal to 1 is f1 plus f1 minus divided by 2. So, 0 plus 1 by 2. So, what is the integral at x is equal to 1? Let us just see. So, we will put here x1, we will get cos alpha. If we put cos alpha into 0, so cos 0, that is 1, and this will be 0, cosine 0, and 1 minus cos alpha. So, this is just 1 minus the integral, we have 0 to infinity with 1 over pi, and 1 minus cos alpha over that pi and alpha square d alpha. So, integral of this as half. Okay. So, we continue the next example. Determine the Fourier integral representing this function f x 1 and 0 when x is between 0 and 2, and when x is less than 0 and x is greater than 2, it is 0. So, between 0 and 2 the function is given by this 1 and then 0, and this side also we have 0. So, further we show that this integral sine alpha over alpha d alpha is pi by 2. So, it is a very similar example what we have seen this. So, we get this a alpha 1 over pi minus infinity to plus infinity and f u cos alpha u du. So, we have 1 over pi and function was defined 0 to 2 only, other than this it was 0. So, we have cos alpha u du, and that we can simplify to give sine 2 alpha over alpha. Similarly, the b alpha we get 1 over pi minus infinity to plus infinity f u sine alpha u du. So, this is 1 over pi 0 to 2 and sine alpha u du, and then we have cos alpha u over alpha. So, we will get this pi alpha 1 minus cos 2 alpha. So, this f x we can represent by this Fourier integral 0 to infinity and sine 2 alpha over alpha cos alpha x plus 1 minus cos 2 alpha over this alpha, 1 over pi is there, and then we have sine alpha x and d alpha. So, we have 1 over pi 0 to infinity. We can again combine these two. So, cos 2 alpha and minus cos 2 alpha sine alpha x. So, sine we get alpha and 2 minus x plus this sine alpha x left and divided by alpha, and we have d alpha. So, if we substitute here at x is equal to 1, we have f1 and the value of this function at 1. So, here 0, it was 2. So, at 1 the value is 1, because here we have the point of continuity. So, we will get just the functional value there. So, we have this integral 0 to infinity sine alpha and here also sine alpha. So, we get 2 sine alpha, 2 will take to the right side. So, 2 over pi will be pi by 2 and the function value at 1 and this is 1. So, this integral value is pi by 2. So, this was the this was the Fourier integral representation of a function, and now we will go for the particular cases, that's Fourier sine and cosine integrals, and it is basically the idea what we have Fourier sine and cosine series. So, if this f x is an odd function, that means this f x is minus f x, f minus x is minus f x, odd function. In that case, this a alpha, we have minus infinity to plus infinity and f u cos alpha u du. So, f is odd, then this is even. So, we have an odd integrand and minus infinity to plus infinity will give 0, and this b alpha will be 2 over pi and 0 to infinity instead of minus infinity to plus infinity, because now the integrand is even function sin alpha u du. So, this is odd and this is odd. So, we have even function. So, the integral will be 2 over pi and f u sin alpha u du. So, in that case, this Fourier sine representation of that function will be given by 0 to infinity b alpha and sin alpha x d alpha. And similarly, if the function f x is even function, then b alpha will be 0 and this a alpha will be given by 2 over pi 0 to infinity, and we have f u cos alpha u du, b alpha will be 0, and this f x we can represent by the 0 to infinity a alpha and cos alpha x d alpha, and this x is between 0 to infinity. So, let's quickly go for one example. So, we consider this function f x, which is 0, minus 1, 1 and 0. So, 0 when minus infinity to minus pi and minus pi to 0 and 1 when 0 to pi, and this is 0 when x is greater than pi. Okay, so, for this function, if we just look at, so we have 0 less than minus pi, then the function value is minus 1, then we have plus 1 and then again 0. So, this function is an odd function because this value is minus of this value. So, this function is an odd function and then a alpha will be 0. So, solution. So, we want to have this Fourier integral representation, and so a alpha will be 0 and then b alpha if we get, so it is 2 over pi 0 to infinity f u sin alpha u du, and this is 2 over pi, we have 0 to pi simply, and that's value is 1 for f. So, we have sin alpha u du, and this is 2 over pi alpha, we have cos alpha u. So, with minus sign, so at 0 we will put first, we get minus and 1 minus cos alpha pi. Therefore, the Fourier series is Fourier integral representation of Fourier sine integral representation will be given by 2 over pi 0 to infinity 1 minus cos alpha pi, or alpha, and we have sin alpha x d alpha. So, there was a question that what will be the value of the integral at x is equal to minus pi. So, value of this integral at x is equal to minus pi, we will take the average of these two values. So, it is a 0 and minus pi by 2. So, this value will be 0 minus 1 by 2. So, minus half. So, one more example we go. Find Fourier sine and cosine integral representation for this f(x) 1 0 for 0 to pi, and when x is greater than pi it is 1. So, this function is given, it is defined from 0 to infinity only. So, we have one value, and then when greater than pi is 0. So, this is the function given, and we are interested to find the sine and the cosine integral. So, for the sine integral we will have the the odd extension, and for the, so let us just go for the Fourier sine representation. Fourier sine representation, in this case, so we can extend that function which is given here as an odd function. So, this and then 0. So, now for this function, or the new function, this is the continuation to that function, the given function in the left axis. So, we have this odd extension, the odd extension, and in this case we will get sine integral representation, because for this function a alpha will be 0 and we will get only the f(x) 0 to infinity b alpha and sine alpha x d alpha, and for this we will calculate this b alpha, that is 2 over pi 0 to infinity f u and sine alpha u du. So, this integral, so the f u we can go 0 to pi, and we have sine alpha u du. So, this will be 2 over pi 1 minus cos pi alpha over alpha. So, this Fourier series representation, Fourier integral representation 0 to infinity, and we have this b alpha 1 minus cos alpha pi or pi alpha divided by alpha and sine alpha x dx, or it is a 2 over pi 0 to infinity 1 minus cos pi alpha over alpha and sine alpha x dx. If you want to see the value of this integral, what will be the value of this integral? So, at x is equal to 0, x is equal to 0, or x is greater than pi, or x is greater than pi, x is equal to 0 or x is greater than pi, the value would be, so here the value will be 0, and at this point if we take the average, it is going to be again 0. So, the value of this function will be 0, and at x is equal to pi. So, at x is equal to pi, we will take the average. So, we have 1 and we have 0. So, 1 plus 0 by 2, that means 1 by 2, and what left now between 0 and 1. So, if x is between 0 and pi, then the value is 1, value is 1. So, for different values we can get a particular integral and can find the value of the function. So, now the second, Fourier cosine representation, Fourier cosine representation. So, in this case we will extend this function as an even function. So, it is an even extension, and in this case now b alpha will be 0 and this a alpha we can calculate by 2 over pi and 0 to infinity f u cos alpha u du. So, we have 2 over pi and 0 to 1 cos alpha u du, or 2 over pi we have sine alpha u over alpha sine alpha u over alpha with negative sign, and 0 to 1. So, we have 2 over pi with plus only, because the integral of this cos will be sine alpha u over alpha 0 to. So, we have 2 over pi and we have sine alpha over alpha. Okay, and then this f x we can represent by this 2 over pi 0 to infinity, and this so our function was defined between, it was 0 to pi. So, we have to have here 0 to pi. So, in that case it will be just pi alpha. So, this Fourier representation, Fourier integral representation will be sine this pi alpha and cos pi alpha and divide by alpha d alpha. So, if you want to have the value of this integral, so it will be 1 as usual when this x is between 0 and pi. So, in this case at this 0 also we have the value 1, because its a function is now continuous. At that point also we have the half value at x is equal to pi, and we have 0 when x is greater than pi. Okay. So, now we go to a very important topic of this, which is just an extension of this study what we are doing now. So, Fourier cosine and sine transform, Fourier cosine and sine transform. So, what we have, this Fourier integral of a function f x, we assume this equality there. So, 2 over pi, in general we have this the average value 0 to infinity, and let us write in this form. So, this is the first case for the cosine one. So, if function f x is an even function, then this Fourier cosine representation will be 0 to infinity and 0 to infinity f u cos alpha u du, and then we have this cos alpha x d alpha. This is a alpha and this is, so 2 over pi this and this. Now, if we set here, if we set that f cos, we denote this f c f or f c hat function of alpha is square root 2 over pi, and this integral 0 to infinity f u cos alpha u du. So, basically this part, and we have taken here square root 2 over pi du. So, this part if we name it f c alpha with this hat, or later on we will call it the Fourier cosine transform of f, and then what we have, the f x is equal to again the same factor left over there 0 to infinity f hat c alpha and cos alpha x d alpha. So, this is called the Fourier cosine transform of f, and this is here is called, we can also write this f cosine inverse of this f hat c alpha. So, this is called the Fourier or inverse Fourier cosine transform of FC alpha. Okay, so now same for the sine representation. So, similarly it follows for odd functions. For odd functions, what we have that Fs of f is Fs alpha denoted, and we have 2 over pi and 0 to infinity Fu sine alpha u du, and we have similarly F s inverse f, which is Fx, and we have 2 over pi, we take 0 to infinity F hat s alpha sine alpha x d alpha. So, this is the Fourier sine transform, Fourier sine transform, Fourier sine transform, and this is inverse Fourier sine transform. There are different versions available in the literature. So, we can have here completely 2 over pi and then can remove here this factor or vice versa. So, but we will follow this that the same factor is sitting for both. So, we now quickly go for some important properties of these transforms. Properties of Fourier sine transform and Fourier cosine transform. So, the one linearity which holds for all these integral transforms. So, we have A f plus B g, and this will be A the constant times the Fourier cosine transform of f plus B the Fourier cosine transform of g. Or similarly for the sine, if we have A f plus B g, we have A f s plus B f s g. The second, which is an important property, and we will not discuss more properties for this sine and cosine transform, but this will be useful. So, let f x be continuous and absolutely integrable on x axis. Also, we let this f prime x be piecewise continuous on each finite interval, and this f x tends to 0 as x tends to infinity. Then, so this is a similar condition what we have, this left and right derivatives exist. So, this is a slightly stronger condition than that. So, what we have in this case, that the Fourier cosine of the derivative will be f Fourier sine of the function f minus 2 over pi and f 0, and we have for f sine f prime x as minus alpha Fourier cosine transform of f. So, let us go quickly to the proof. So, we have Fourier cosine transform of f prime x square root 2 over pi 0 to infinity f prime x and cos alpha x dx. So, we have 2 over pi, and then we take the integrate by parts. We integrate by parts here, cos alpha x limit 0 to infinity minus 0 to infinity, we have f x and sin alpha x into minus alpha, because this is the differentiation of this, with the minus sign will appear. So, what we have 2 over pi, as x approaches to infinity, this f will go to 0. So, we have minus f 0 and minus minus plus alpha, and this is the Fourier sine transform. Fourier sine transform with this 1 over. So, we take this 2 square root 2 over pi with this term, and this is Fourier sine transform of f x. So, this was Fourier cosine transform of f prime x. So, we also have if we go for the second order derivative, that means f prime x. So, we have minus square root 2 over pi first derivative by this formula, this was for first derivative, and plus alpha f sine and f prime x. And now we assume here, in addition to f prime also goes to 0 as x goes to infinity, then only we will get this, and then we apply 2 over pi f prime 0 minus this. We will see in a minute that f sine of f prime or a function is minus alpha square, and f cosine we will get f x. So, this is this, and similarly we can go for the sine function. So, for sine we have f sine and the f prime x. With the similar trick we can have, we will get minus alpha f cosine f x, and for the second derivative we have the f sine for the second derivative of x is square root 2 over pi alpha f 0 minus alpha square f sine f x. So, here we have introduced this Fourier cosine and sine transform. We started with the Fourier integral representation of a function, and then we introduced this Fourier sine and cosine transform. So, in the next lecture we will continue with this Fourier sine and cosine transform with the help of examples, and then go for the Fourier transform. So, more on this in the next lecture. Thank you. Goodbye.